Hey everyone, today we're going to talk about gel destaining and Western blot, which are experiments for Lab 10. So this is our second half of the SDS page and Western blot lab. We're going to focus a bit more on the theory behind antibodies, which we use to visualize a Western blot. So by the end of this lab, you should be able to use a molecular weight ladder to predict where protein of known size should migrate, and then use the size to identify the protein on a gel. You need to use the distance migrated by your sample and relative to the ladder in order to construct a Lamb plot to determine the molecular weight of a particular protein in your sample. So specifically your protein of interest. So you're going to actually find the size, estimate the size of LDH based on a Lamb plot. And then you're going to also have to use, so in addition to using your Kumasi stained SCS page gel quantitatively, you're going to have to use a combination of your Kumasi stained gel and the Western blot qualitatively to determine if your SDS purification was successful. So first things first, what is an antibody? So let's talk a bit about, let's do a bit of an overview here. So an antibody is a protein that recognizes and binds a particular antigen. And this is a highly specific interaction. And your immune system makes these proteins to combat foreign substances. And so if some kind of weird chemical enters your body, that would be an immune response against that chemical. So experimentally in the lab, how do we make antibodies? Because certainly we can't use ourselves. So what we do is, or in particular, antibody companies will do this. You inject an antigen into an animal. Very commonly, some of these animals can be rats, rabbit, sheep, goat. And then what happens is these animals develop an antibody against the antigen. And then you can purify those antibodies and then sell them. And again, just a quick note to emphasize that these are very specific interactions. So an antibody is only going to recognize a particular antigen of interest. So what does an antibody look like? So I just have a cartoon structure of an antibody here, but they have a few key parts. So in purple here, these would be the heavy chain, and then the light purple, guys, these are going to be okay, let's change the way we highlight that. Okay, the light purple parts, those are going to be the light chains. And those are named because the heavy chain has a higher molecular weight than the light chain. But then on top of that, so there's the heavy chain and the light chain, but the antibody has two other key parts. And so kind of the stem up here that's half of the heavy chain, that part of the antibody is going to be specific to the organism. So all rabbit antibodies are going to have the same top part, whereas the bottom part down here, this is the part that's specific to the antigen. So with every antibody made in a rabbit, the top part is going to stay the same, but the bottom part is going to change in structure depending on the antigen that it's evolved to bind. So when we use antibodies in the lab, we use a scheme where we mix what are called primary and secondary antibodies to allow us to detect a particular antigen. And I'm going to do this in the context of, this is a general scheme that is exploited for different systems, but I'm going to talk mainly about the system that we use. Okay, so for our primary antibody, this is a rabbit antibody. So our primary antibody was made in rabbit, and it's anti-LDH, and actually it's anti-human LDH. So the rabbit antibody means it was made in rabbit. So this part is going to be rabbit specific, whereas anti-LDH is talking about the bottom part, and that means this anti means it's going to bind LDH. So this part down on the bottom binds LDH specifically. However, if we just throw this primary antibody on there, it's not going to do us any good, because when we transfer our proteins to the plate for the Western blot, we can't visualize it. So what we have to do is we have to somehow get a fluorophore or like some kind of dye, either a fluorophore or a conjugated one that does a chemical reaction onto the end, so we can visualize where our LDH bands are, and then compare that back to the protein gel. So the way that we do that is actually by making a secondary antibody. And that means the secondary antibody binds the primary antibody. And so this is a goat antibody. That means it was made in a goat, but that's irrelevant. Well, not necessarily. So that means that this part of the antibody comes from a goat. And it's conjugated to HRP, or horseradish peroxidase, or so HRP, and sometimes we've also used alkaline phosphatase. And what this reaction, or what this does, is when we take the secondary antibody and we add TMB, it performs a chemical reaction that turns the band purple. So this secondary antibody allows us to has a enzyme on the end that when you add the enzyme substrate, it makes a color change, but it's only going to make a color change where that antibody is, so therefore only where LDH is. So we know this top part comes from goat. It has an enzyme on the end that catalyzes a color change reaction that allows us to visualize the antibody. Then the question is, how is this guy related to our LDH protein? Well, and where that comes in is the bottom half, or the variable area of the secondary antibody, is anti-rabbit. So that means the specific part of the antibody binds rabbit antibodies. So you can take this guy and it will attach to any antibody, it will recognize and bind to any antibody that was made in a rabbit. So it'll recognize our rabbit anti-LDH antibody, but it would also recognize any other rabbit antibody. So the advantage of this system is that when we use the primary antibody, that allows us to tune for specificity. So that allows us to select a particular, to bind and select a particular antigen, which in this case is LDH. You could also use it to bind a different enzyme with a different antibody. whereas the secondary antibody allows us to visualize our target and figure out where on the Western blot and which lanes and what the size is of our LDH target. And again, so what this does when we add these antibodies to our Western blot, what this allows us to do that we can't do with an SDS page gel alone is to verify the identity of LDH. Because hopefully, if your marker transfers, you'll be able to confirm that the LDH band is at the same place in terms of size that you would expect it to be on the SDS page gel. But then this would allow you to see and confirm which band in the SDS page gel is in fact LDH. So with the SDS page gel, you can see where if there's a protein at the correct molecular weight, it allows you to see how many other proteins there are and whether or not your sample is pure, whereas Western blot in tandem, Western blot can tell you the identity, and then with the Western blot and the SDS page together, you can get an idea of both the purity and confirm the identity of your sample. So talking a little bit more about the Western blot in detail, there are several points there are points in the purification where you have to rinse the membrane with the Blotto solution. So I wanted to talk a little bit more about just what the Blotto solution is. So the Blotto solution is a solution of dried milk or freeze-dried milk, but it's essentially the casein protein. And we use casein because it's really cheap and you can get a lot of it in bulk. And so what you do is you're essentially washing the membrane with a high concentration of protein. And so this prevents non-specific binding of other protein of your antibody to other proteins and the membrane. Because what you have to realize, and one of the reasons why you're going to have to take great care with the membrane in this lab when you're using like your gloves and your fingers, is because the membrane is really sticky to protein. So it's not physically sticky, but proteins like to stick to it. And so if you were to just throw your antibody on the membrane, and if you were to develop it, the whole membrane would turn purple because your antibody just non-specifically glommed onto the whole sheet. So what happens with Blotto is Blotto takes up all the sites on the membrane that aren't taken up by proteins that are in your sample. So then what happens is the antibody isn't going to bind the membrane because the milk proteins are taking up all the spots on the membrane, and therefore it's only going to bind to the places that have LDH. So after you've done the Blotto solution at the beginning, and then you've applied the antibody, or after the Blotto solution and after the antibody, after any time you try to put a protein on the membrane, you wash with TBST. And so the purpose of TBST is to remove excess Blotto solution. And also later remove excess primary and then secondary antibody. And removing those excess proteins is what allows you to get nice defined bands on your Western blot, instead of in the case where if you were preparing, like if you weren't to apply the Blotto, it would be completely purple. but the combination of using the Blot solution, so blocking the nonspecific binding of the antibodies, and then removing any excess blotto protein and antibody from the membrane is what allows us to get nice defined bands. So ultimately, our goal is so how do we want our blot to look? Okay, so a quick thing to run over before we talk in more detail about this is a reminder that when we did gel filtration, you literally took LDH and you ran it through the column. You didn't do anything to the structure, so the LDH quaternary structure was intact. And so most of you guys got a molecular weight of around 150 kilodaltons. However, we have to remember that for SDS page, because our immunoblot is coming, our Western blot is coming as an SDS page gel that has been transferred to a membrane. Well, at SDS page, we're adding SDS, BME, beta-mercaptoethanol, and then heat. And we have to remember this is unfolding the sample, or unfolding the protein, and then we're disrupting quaternary structure of LDH. So remember that in our gel and in our Western blot, we're going to be seeing LDH showing up as a monomer. So if we were to look at our, and so again, that would be a monomer of around 37.5 kilodaltons. So what this would look like is if we had our Western blot, so the ladder is going to show up. So you have, again, those different colored proteins because the proteins that are in the ladder are chemically conjugated to dye molecules. What we would see is that as we go from the 40% cut to IEX to our affinity, hopefully we would see one band in each lane, and it would be around 37.5 daltons. And as we progress through purification, our sample would become more concentrated. And so ideally, the band corresponding to LDH would grow in intensity. So a higher concentration. So even though your total milligrams of protein might be going down, the concentration of other stuff and ultimately the volume of your sample is going to go down. So in theory, your LDH concentration should increase as you go through purification. So again, that hallmark is the fact that you only see one band corresponding to LDH. It's the right molecular weight, and the band intensity increases with progressive purification. And then one last question I want to answer about the Western blot is, first of all, again, to clarify that our primary antibody is anti-human LDH, even though we're using bovine LDH. And why is that the case? That's because, well, first of all, I don't want to say it's out of laziness, but it's out of convenience. And that's because not human anti-human LDH is commercially available. We already can find it easily on the market and for a reasonable price, but also human LDH has a 95% sequence similarity to bovine LDH. So there's a lot of sequence overlap between human and cow LDH. You'll learn a little bit more about that in the next lab. And so because they're so similar in sequence and therefore in structure, the antibody for human LDH actually also recognizes bovine LDH, which is why we're able to use it. So, just FYI. So you're also going to be destaining the SDS page gel in this lab. And so we talked a little bit about what Western blot can tell us. So let's describe more about the SDS page. So with the SDS page gel, instead of transferring and then using a very LDH specific detection system, we're using a Kumasi dye stain here. And if you remember, we used a Kumasi dye variant in our Bradford assay, and just as a Bradford assay detects total protein or detects all the protein, Kumasi binds all the protein. All right, and so what this can tell us is how pure is our sample. So, are there other proteins present? And then it can also tell us the size of our protein. So in this case, it can help us determine whether or not our protein of interest is in fact 37.5 kilodaltons. But one thing an SDS page cal can't do, which is why we do the Western blot, is it can't tell us the identity of our protein, and that's why we need to use SDS page and Western blotting together for the most full. You can also use like mass spectrometry to confirm the sequence, but for a quick and dirty and easy way to do it for a biochemist is to do a Western blot and an SDS page gel. Okay, so we're using a combination of Western blotting. We talked about what a successful Western blot purification would look like, but what would a successful purification look like on an SDS page gel? Okay. All right, so let's draw out our SDS page gel here. We have ladder, we have 40%, we have IEX, and we have affinity here. All right, so we've got our ladder on the far left-hand side. And so at the very beginning, we start off with a 40% sample. We're going to have a lot of bands that correspond to protein. And again, these are blue bands because Kumasi is blue. Okay, but as we progress throughout the purification, in theory, the number of bands should decrease. So let's say this is LDH right here. And then ideally, by the last step, there won't be any other proteins, and the intensity of the LDH band will increase or will be enriched because our LDH solution is becoming more concentrated. So in theory, as you progress throughout the purification, the amount of other proteins is going to decrease. Ideally, there wouldn't be any other proteins in your final sample. So for a sample to be pure, it needs to be like 95 to 100% your enzyme. All right, so you should not be able to see any other bands. So again, ideally, you should only see a band corresponding to LDH. Another thing is that LDH should be enriched. And we talked about that a little bit with the Western blot, but the band intensity should increase. If your purification is successful, by the time you get to your last sample and you're only going to have a few mils or a few hundred microliters, that band intensity is going to be huge because you're going to have a really concentrated sample of LDH compared to like your first ammonium sulfate cut where you had 200 mils and a little bit of LDH. But this, as you know, we're in a teaching lab. Things often don't turn out quite as we would like or quite as we had hoped. So if you don't have a pure sample, how do you know that you're at least going through the process of somewhat purifying your protein? And again, that's where is LDH being enriched? So is your LDH band going up? Are the numbers of other proteins decreasing? And then those are kind of the questions that you have to ask yourself. So if you look at your gel and LDH is not the only band in your affinity sample, the questions you need to be asking yourself are, okay, so obviously this was not a successful purification, but is LDH enriched, and are the number of other proteins decreasing? Because then you're at least partially purifying your sample. And that's better than nothing, because at least you have somewhere to start. Okay, so I mentioned that we can use an SDS page gel to quantify the size of a sample. And so you can do that just by looking at the location of your sample relative to a ladder, but you can also use a Lamley plot to quantitatively determine the molecular weight of our sample. So again, we can use it to confirm the molecular weight of LDH. And so the way that we do this is, so when you have your gel, you're going to run your gel, and you'll notice, so here's your ladder. You'll have your sample. And then you'll notice at the bottom of the gel, there's going to be a blue solvent front. Okay, and so what you do is you set the bottom of you take a ruler and you set the bottom of your ruler to 15. So if you have a 15 centimeters on your ruler, put the bottom point there. Then you're going to mark the location of the bands in your ladder, and then what you think is your LDH sample. So oops, that's not LDH. So if this is your ladder, and then this is where you think LDH is, so you mark, okay, this one's 14 centimeters, this one 13 centimeters, all the way up to 1 centimeter at the top. So that's your solvent front. Solvent front, it's going to, and that chemical that's going to be at the solvent front is bromophenol blue. Okay, and so then what you're going to do, and so then you'll also measure whatever that number is for LDH. Then what you're going to do is you're going to find the RF for each band of your ladder. And so if we're solving for the RF of this guy here, that would be, okay, so this band migrates 13 centimeters, and you divide that. So the migration of the band, and then you divide it by the migration of the solvent front. So that would be 15 centimeters. Oops, the RF, by taking the distance migrated by the band of interest divided by the distance migrated by the solvent front. And this is a unitless ratio. All right. So you calculate the RF for the relative migration for every band in the ladder, and then you can create a calibration curve like we did for our Bradford assay. So what we'll do is we'll graph the RF on the x-axis and the molecular weight of the proteins on the y. You'll know the molecular weight of the proteins from a handout or a picture that we give you that'll list the molecular weight of each protein. And so then we can graph, or the molecular weight, the log of the molecular weight. And so then what you'll do is there will be a line. And then you can fit it linearly. So you'll get out a y equals mx plus b equation. And so then you'll go back and you'll measure and calculate the RF for LDH. And again, the LDH is our x here. So you can plug in the RF for LDH, plug it in for x, and then solve for y to give you to approximate the molecular weight of LDH. So things to keep in mind when you're comparing the results for the molecular weight that you get from your Lamley plot versus the results that you got from gel filtration. Remember, with the Lamley plot, we are looking at a gel where LDH is denatured, which means we're not going to be taking quaternary structure into account. Whereas for, go away, oh no.